So thank you much for organizers for inviting me here, and it's a great honor speak at the birthday conference of Alec. So I started to kind of do research with him, like 5 years ago. Also, like after
Louder, please.
after an email exchange, and I said, what should I say? But like, yesterday was such a great talks about Alec during this conference or during this banquet. So I kind of I learned something that I'm not alone. So you know what I mean. Okay. So this is mainly I will speak about results with Gabriele, but in the end I hope I will come to results with Alec. So I will start with just with the definition that like we have spherical Euclidean or hyperbolic surfaces with conical singularities. It's a surface with a complete metric of curvature 1, 0, or -1. Yeah. If you think about something, I hope you can see something like this. Yeah, like this is my say sphere. I have metric of curvature 1, but also singularity. And you see, like the singularities, they have angle. Because basically, if you draw a cone, so this is like a typical like Euclidean cone that you are used to. And if you take a Euclidean cone, you can take a circle of radius epsilon, yeah, and then it will have length 2 pi theta epsilon, where like theta is in the conical angle. And if you have like hyperbolic geometry, you will have this formula, hyperbolic sinus, but again you will have this theta. And in spherical geometry, you will have this formula. But again, what is important is 2 pi theta, so there is a conical angle. And I'm mainly interested in spherical surfaces. I will explain why. But examples what you can imagine, like of this type of behavior. So you take a two-dimensional sphere as 2, yeah, round as 2, and you quotient it by, you rotate it by angle 2 pi divided by n, and quotient. And then you get something which is called like orbifold. So this is one example. Here the angles will be 2 pi divided by n quotient. And other thing is other example, you can take, instead of taking quotient, you can take a ramified polar. Again, you take your sphere as 2, you map it to F2 by the map, like it's a complex sphere, so z goes to z power n. Yeah. So this is the map. And then here you have a round metric. You have a round metric, so you can pull it back. You can pull it back on the sphere, and then what you will get something like, which is very, very hard to draw, but you should think like a pumpkin. Yeah. So it's like angles 2 pi n, 2 pi n. So that like 2 examples that are very natural, but they're more. Now, important thing is that if you take any such surface, you can think about it just like built from triangles. And this is how I think about it. Yeah, you just take a bunch of triangles and glue them by isometry, and you get a metric. And of course, like for example, like if you take a tetrahedron, yes, the tetrahedron is glued from 4 triangles, then it's an example of Euclidean metric. And here you have conical singularities. While at edges, you don't have anything, like at edges are smooth. And then important thing is that surfaces with conical singularities are, in reality, they're compact Riemann surfaces. So this is like quite easy to see. Of course, here we have like metric of curvature 1, so it's just a part of a round sphere. And here it's easy to introduce complex coordinates. So basically, these are in reality surfaces, Riemann surfaces. Okay. So this is what you need to know. Now, next thing is like kind of very important is, suppose you have a surface, and you surface with conical singularities, and then there is a Gauss-Bonnet formula. So you have this surface with conical angles 2 pi, then here k is curvature, and 1 pi times area, 1 over 2 pi times area times curvature is equal to early characteristic of a surface plus sum of defects. We have this formula. And this is why you see kind of moral of this formula is the following, is that if you compute this number, it will have a sign. It will be either negative, 0, or positive. And the sign will tell you what kind of curvature you can have. For example, if you have here the sum is equal to 0, then you know that your surface can only have metric of curvature 0. If it's positive, it can have only a metric of curvature 1 and negative -1. And like so a little bit like more definitions that I need to set up the scene. So Mgn is the moduli space of Riemann surfaces. So you take all Riemann surfaces of certain genus, and you have like with n marked points. So it's a classical object, like very important object in algebraic geometry, produced by Riemann, and this is certain orbifold, complex orbifold of dimension 3g minus 3 plus n. It's an object of complex geometry. And what is of interest to me is this moduli space of spherical surfaces. So again, I fix the genus, I fix the number of points, and fix the angles. And then we consider just the space of all such metrics. It's like not hard to see that you can introduce a topology on this space, like say, like Gromov topology. And we want to understand the space. And there is one like important thing. There is a map from the space of spherical surfaces to the space of Riemann surfaces. And kind of this map is called forgetful because it forgets the metric. Okay, now what are the main questions? So like, how does this space of spherical metrics look like? What is dimension? Like, is it a manifold? What's the topology of the space? And next, how does the forgetful map look like? Yeah. So this is a map from like if you forget the metric and you just remember the Riemann surface. Okay. So here's the kind of schematic picture. So here I drew like this. I drew here the space of spherical surfaces, and here the space of like Riemann surfaces. And I forget the metric. When I go from here to here, I forget the metric. And you want to know like everything about this map. Is it like surjective map, degree? Is it finite map? And maybe kind of the main let's say idea is that usually what people do, they consider the opposite direction. Okay, you start with a Riemann surface and you want to construct a metric. And this is what is like Poincaré did. Like he said that for every Riemann surface there is a metric of constant curvature, and this is a solution to certain partial differential equation PDE. So I never think about this PDE. I copied this from really good lectures of Alec on spherical surfaces. So basically, if you want to solve a PDE, you write a metric like this, G is equal to rho z dz, and then you need to solve this equation, kind of Monge-paired equation, like Laplacian -1, and this is the behavior of the metric. Okay, but for us, kind of what is important is that so this PD is very complicated. It's just kind of extremely hard to solve. On the contrary, the space of solution is in some sense more simple because you can think about this as just, as I said, a surface is glued from triangles. So basically, you can construct it by hands. The space of solutions can be constructed, and instead of like trying to solve this PDE, you try to understand the math. And so this is the kind of philosophy, let's say. Okay. So now, so you can ask like why spherical surfaces? Yeah, why spherical surfaces? Why not hyperbolic and Euclidean? And of course, because this was understood very well. So there is a theorem of Troyanov-Markovan, which basically tells you that if Gauss-Bonnet inequality is satisfied, so this sum is negative, then for every Riemann surface with these marked points, there will be a unique metric of curvature -1 with given angles at the points. So this is like analog of uniformization theorem. For every Riemann surface of genus more than 1, you have a metric of curvature -1. And if there is a unique, you see, a conformal hyperbolic metric, yeah, then what we see is that these two spaces, space of hyperbolic metrics and the space of this space of Riemann surface is the same. So in other words, kind of this question that we have here is just like kind of triviality. I mean, this map is kind of one-to-one map. It's a one-to-one map, nothing to say. But for spherical surfaces is not like this. So basically, for spherical surfaces, really very, very little is known. Like what is the nature of this map? Like when is it injective or whatever, surjective? And there is nothing like, for example, you fix angles. Maybe you don't have a metric. Maybe metric is not unique. And I just want to give you one example, like kind of to convince you that you should not expect uniqueness. Okay. That the metric should not be unique. So this is like an example is like this. So this is a picture. Okay. So like usually, so I draw it like a snowman, but now it's not. It's a caterpillar. Caterpillar. Yeah. So because otherwise it wouldn't fit. So like, so you see what we did here. We took three spheres here, and we glued them. Like we made like you see like in the sphere, you can make a cut. Yeah. Like this. And you have another sphere, and you can like glue them together, and you get like a new surface. So now we took like here three spheres, yeah. And it's one construction, but other construction is like this. You see, like we take a metric with angle 6 pi, which exists like as a pullback, and then we slightly kind of split this angle 6 pi in two angles of 4 pi, yeah. And then what you see, like metrically, this surface is different from this. It's kind of obvious. I mean, metrically, there's no way they're the same, but conformally, them the same. You can kind of see it. Basically, you can convince yourself. It's like if you do something like this, then your sphere is almost degenerate, yeah, because like there is a like or a big circle here, big cylinder, and here again, like you will have a sphere with 4 points with a very small double ratio. So basically, these are two surfaces isomorphic, but metrics are definitely different. And this is kind of the first sign of the fact that things go differently. Okay. So now I want to just I need some kind of definitions a couple of definitions. One is the definition of development map is like this: is that you see, if you have a surface, if you have a surface, let's say with spherical with conical singularities, it has a metric of curvature 1. So you can start to map it the round sphere S2. You map it to the round sphere S2 locally as a metric. And then you start kind of to extend this map by isometry. And in the end, what you will get a map from the universal curve of the surface to the sphere. So this is called the development map. So it's a like multivariate locally isometric map. And then in a similar like way, you have monodromy. Monodromy basically when you take a path on your surface, you start to develop along this path, and the end kind of you don't come back, but you come somewhere else, and you get a certain transformation from SO3. So now, kind of first lemma is like this. So it's a lemma of Troyanov that. So we want to kind of maybe understand maybe the simplest case of such metrics. So suppose we want to understand spheres with two conical points of certain angles. So then Troyanov, so like we want to understand all spheres like this. Yeah. And then Troyanov says that what Troyanov says is that in this case, these conical angles should be equal to each other, and moreover, if the angle is not integer, then your sphere should be S1 symmetric. Okay, but if your angle is integer, then your sphere comes from the universal from the cover to the round sphere. And so here's the proof. Basically, it's just kind of the proof is really it's indeed like a elementary school proof. So what you do, yeah, you take your sphere with two conical angles, and you cut along a geodesic, yeah. You cut along the geodesic. Then what you get is a disk. The remainder is a disk, yeah? And this disk, you can send it by development map. You can send it to the round sphere, okay? And then the boundary of the disk will go to something to a polygon with two sides, yeah? Polygon with two sides on the sphere. But there are not so many polygons with two sides on the sphere. Basically, either like this, you have just two sides which are shorter than pi, and they coincide. And this is the example. Yeah. Or you have polygon with two sides, but where both sides have length pi. Yeah. And so this kind of gives you. So in this case, you get angle can be arbitrary, and you get spherical. You get a spherically symmetric metric. That's one symmetric metric, and here you get a metric which kind of like a ramified cover. So this is the theorem of.
Can I ask a question?
Yes.
Angles are supposed to be positive, right? So
That's right. That's right.
In the lemma, actually, it means the natural number.
You're right. Thank you very much. Yeah. Yeah. I should have said the angles are positive. You're right. So it should be a non-integer. Yeah. And theta. You're totally right. Yeah. Thank you. So like in hyperbolic geometry, angles can be less than 0, but here they should be positive. Okay, so this is like, see, we saw like we proved the result. I think from the 80s. There is only one metric like this. Oh, so the description, we have a description of metrics with two conical singularities. By the way, please pay attention. There is no metric on a sphere with one conical singularity. Yeah, because like if you have like one conical singularity, you can say you have a sphere with one angle to pi theta and y angle to pi, and the same proof shows that it doesn't exist. Okay, so now we go back like 120 years ago, and we ask a question basically, which was asked by Felix Klein and answered, and also like almost answered, and Alec also kind of contributed to the answer to this question. And the question is like, again, this is like elementary like a kind of high school question. So like a question like this. So you take a two-dimensional sphere, yeah? And you take 3 points on the sphere, yeah? And you take a triangle, like spherical triangle. And suppose it has angles pi theta 1, pi theta 2, pi theta 3. Okay? And so what can be said about these angles? What can be these angles? So like for Euclidean geometry, we'll remember like sum of 3 angles should be equal to pi. But what happens here? What answer do we get? The only thing like we will be also interested in the cases when these triangles are not convex, but they can have arbitrary large angles, as Andrei was mentioning. And the answer is like this. So like I want to kind of explain to you what is the answer. So spherical triangle exists. Well, these angles exist if and only if the following inequality holds. Okay. So Z even is like all integer points such that the sum is equal to the sum is even. And then and this L1 distance. So L1 distance from basically L1 distance from your angle theta 1, theta 2, theta 3 to Z1 should be greater than 1. But okay, it's impossible to visualize it without picture, but here's the picture. Okay, so just I will now stop like at this picture. Okay, so first let's focus on convex case when all these angles are less than pi. Yeah, suppose we have a convex triangle. Yeah, so what do? We plot theta 1, theta 2, theta 3 inside of the cube. Yeah. And this cube is like 1 by 1 by 1. And we want to know for which points inside of the cube there is a spherical triangle. And the claim is that the triangle exists only more or less if and only if you are inside of this simplex. Okay, so this is a simplex. And this simplex, you see, it has like four faces. Yeah, so there should be 4 inequalities. And one inequality is easy, is like so this face is just Gauss-Bonnet formula, is that you know, this is the area of your triangle, and the area should be greater than 0. And so this is one face. But what about other faces? Like there are 4 faces here. So other faces are like this. So you see, like if you have a triangle, you can extend it to a bigone or digone. And this has area 2 pi theta 1. Yeah. So you get like four faces. Okay. So here we did like everything with angles less than 2 pi, convex case. But then you see you can have triangles like this, triangles like this. And if you plot these points inside of the 3-dimensional space, you get like this pretty picture. You get the collection of these simplices, tetrahedrons. You kind of start to reflect them, yeah? You reflect them like this, and you pave the whole 3-dimensional space. So basically the answer, you have a spherical triangle if and only if you're inside of these simplices. Okay. So now we see this more complicated case of space with 3 conical points. And now, so basically, I will start to prove or kind of explain some theorems. And I just want really kind of to formulate a question, which so just how to say. So this, you see, this picture is kind of symbol of this activity. Yeah, the simplex is kind of one important picture that you have to have in mind, or one important question. But here's the second question, which is like, again, it looks totally trivial, and it's kind of exercise, which you can try to solve. So questions like this. So the main kind of thing here is to formulate the statement. So suppose you have a polygon, yeah, a topological polygon with even number of faces, 2 n faces, yeah. And now you want to glue a surface from it, okay? And how you can do this? You just identify sides pairwise. Okay? So we all know this picture. So you can glue a surface from a polygon, but there is one condition, just one condition, that you want to glue this side so that all vertices are identified. So all vertices are glued together. Everything's glued together. Okay, so this is the condition. So the question is the following: which surfaces can you get this way? It's a kind of question in mathematics. And the answer is kind of one might maybe think that you can get like all surfaces, but this is not the case. So basically, just here, like I show you. So this is like this way you get the RP2, yeah. You glue this edge with this edge, yeah? You get RP2, and notice that this vertex and this vertex are glued together, yeah. And if you take this rectangle, you get a torus. But what you don't get is, as you can maybe imagine, you don't get a sphere. There is no way to glue a sphere this way, yeah. And this is kind of hugely important for all this activity. I'll just let's say answer everything except S2. And here's a corollary from this statement is like this. So like remember we're interested in the space of in the modular space of spherical surfaces. Yeah, we're interested in this space, and here's the theorem that suppose that we take a genus, positive genus, yeah, then and suppose this Gauss-Bonnet formula holds, then there is always a surface of genus more than 0, this surface with these conical angles. So in this case, the modular space is non-empty. As you see, like for spheres, this is not the case. So it only works for genus greater than 0. And I want to give a proof. The proof is like this. It's kind of, it's not hard. So you take a kind of, one step is really trivial. You take a bigone. You see, this is a spherical bigone with this angle. Yeah. If you have a bigone, you basically use the solution of this problem. You subdivide it like in intervals, and you glue together a sphere or so a surface. And this surface will have just one conical singularity. You will not get a sphere this way. You see, the sphere cannot be get. But if you have one conical singularity, after this, more or less, kind of you can perturb it. So you can split it back in other angles. So what does it mean to perturb? So imagine that you have like an angle, yeah. So this is a certain angle, and then you just kind of make a mess, and so this angle becomes this collection of angles. The proof is not kind of so trivial. So basically, the hard bit in the theorem is to prove that you can really split and extend it to the whole how basically you can deform the singularity, but also the surface with its singularity. Okay. So this is for kind of yeah like for if you are like if you are studying an object, you want it to be non-empty. So this is important. The moduli space is non-empty. But what about like genus G? Genus G equal to 0. What about for spheres? So basically, we want to like see something of this story for higher genus, and for larger number of points. And the answer here is the following theorem. So again, you do something similar. You take like L1 norm in Rn. This is L1 distance. Now you take its odd points. Odd points are just points where the sum of coordinates is odd, and then you have this theorem. So if you have a spherical metric of a conical angle like this, then two inequalities holds. Inequalities holds, and more or less you have kind of the converse. That what we proved that in case you strict inequality here, then you always have a metric. And the case when you have equality is more tricky, and it was settled by Alec. Anyway, but again, it's impossible to like it's a bit hard to visualize this, but here's the picture. Okay, so just I want to tell you. So what's this? What is this? The distance from a point is more than 1. It's basically that you have a certain octahedron. You see, it's an octahedron in a high dimensional space. And so what you do, you take this lattice, and out of each you cut out like an octahedron of size. And the nice exercise in dimension 3, if you count out all this octahedra, you get back all this simplices. So complement to the collection of octahedra. Okay. So this is the theorem. Okay. So now I will proceed. I will proceed like further. So next result is like this. So you have your like you have your moduli space MGN, and you want to know like for which points of this MGN you have a spherical surface. Yeah, you have a surface with conical singularities. So you want to know this thing. And kind of a bit surprisingly, it turns out that like this is like totally contrary to hyperbolic case. When like in hyperbolic case, for each Riemann surface you have a metric. Here the image. So the image of the part of moduli space for which you can have a spherical metric can be really tiny. It can be like very small. So that basically you have a solution only in a corner of your moduli space. And this usually happens when your surface has one angle which is like very small. So for example, if you have a surface which has one angle which is small, then proportion of the moduli space where you have a solution is tiny. And intuitively, it's quite the idea behind it is quite easy. It's hard to implement, but it's easy. So you see, like if you have one angle which is very small, then you can kind of walk along this angle, and then some way you will find a very short geodesic. You will find a very short geodesic, and if you have a very short geodesic, you will be able to find a thick cylinder. So you cannot kind of you have a conformally large cylinder inside of your surface, so it means that your surface is degenerate. But this is basically the idea. And this is this theorem is also like this result is in contrast a little bit with like so you see this angle is important here that the angle is small, but these other guys who solve this PDE, yeah, like as I described, they are able to produce this matrix for basically for large angles. So basically, if angles are large and you have some kind of genericity assumption, then you always have a lot of matrix. But here, maybe the moral is that PDE can give you a solution, but it's PDE like it's harder than when you don't have solution. PDE kind of doesn't find it, and so you don't know what happens. Okay. So this is one result. Other result is that this space of spherical matrix can have several connected components. Again, it's like totally different from the case of hyperbolic matrix, because for hyperbolic matrix we saw that like the model space of hyperbolic matrix is just the space of MGN, it's a Riemann surfaces. But here is not at all the case. The moduli space of spherical surface can have several components, and I will give you one example. So like so what I say, like this space can have more than 3 power n connected components. 3 power n, of course, probably is not important. It's just some number more than 1. And here is the example, basically. Here's the example, like how it looks like. So you see, so this is my sphere, which has four conical points. And if you kind of look at the picture, you see that that there are like 3 points of the same conical angle. So you can think about this as like I say, it's a polygon, spherical polygon, and you double it, yeah? You have like 3 conical angles which are the same, and one is very small. But then what happens is that kind of this small angle is kind of tangled to one of these 3 conical points, and it can appear either here or here or here. And this is why if you look like on the moduli space of like if you look, this is M04, like M04 is more or less like it's a Riemann sphere, yeah. What M04 is that is a space of collection of 4 points on CP1, and we all know like when we have 4 points on CP1, we can put one to 0, another to 1, other to infinity, and then fourth point will roam, yeah. It will be anywhere. But this is why M04 can be identified with CP1, and the solution kind of the spherical metric exists if and only if you are kind of very close to one of punctures in the CP1. Okay.
It's theta n+3 in the title of your slide, right? There's
Yes.
okay.
Yeah. And I think it's correct because 1 + 3 is equal to 4, and 3 connected components.
You know what I mean? It's like you've got the space of theta 1 to
You're right. You're right.
Still fixing n+3 angles, right? So yeah.
Thank you. Sorry. You're totally right. I missed. Yeah. So basically, like yeah. Sorry. Thank you very much. Yeah. Basically, like 3 angles are like this, and all others are small. Thank you. Yeah, so this is what I meant. Thank you. Okay, but then like so this theorem is to appear is that one statement is that still, even though we can have finite number of components, the number sorry we can have more than one connected component, the number is finite. And this basically follows from kind of follows from a paper of Alex and Andrei on they, you see what they did, they described basically this space of spherical triangles. And what is important that the space of spherical triangles is a semi-analytic set, more or less. And so from the fact that space of spherical triangles is semi-analytic set, you can kind of deduce that the moduli space of spherical surfaces has finite number of connected components. So this is one thing. This is kind of easy. And second statement is, which is kind of harder, is that the picture that you see here, like you see what happens here, is that you have a component and it projects and it contains kind of a it goes to infinity in the moduli space. So this point doesn't belong to the moduli space. And so the statement is that all the spherical, every connected components, when you project it to the modulus space of Riemann surfaces, it also goes to infinity. But for this, we impose the condition that conical angles are non-integer. Okay. So great. So now I come to the bit so you see, like we saw, like moduli spaces, they have different connected components. Like it's not totally clear what they are, but we want to have a, let's say, we want to understand at least one moduli space, yeah? Because like so for spheres with three conical singularities, moduli space is just a point. So it's kind of, it's not a big deal. Point is not maybe so interested, but we want to have second example, which is like non-trivial, yeah. And the second example, which is like next say non-trivial example really, that one can try to understand, is basically you want to consider tori with one conical point, and you want to understand what metrics can you get on a torus with just one conical singularities of angle 2 pi theta. Describe this moduli space. Okay, so how should we think about this? Well, basically, you know, like here's like a warm-up. Suppose we want to construct a flat torus, yeah? So what do? We take a just say flat torus without conical singularities. We take a parallelogram, yeah? We take a parallelogram and we identify its opposite sides. And this gives us like a bona fide flat torus, say with one marked point, yeah? Something like this. So this is a construction of a flat torus, because flat torus is a kind of a limit of spherical ones, yeah? And now, if you want to think about a spherical torus, so what you can do, somehow you see you take on a sphere, for example, you can take something which is like a parallelogram, so it's a polygon. So this side has same length as this side, and then you glue together. So this is an example, and we want to understand all of them. We want to understand all of them, and so now here is the theorem. It was published in 2023. So I want kind of to explain like this theorem. So suppose your angle theta is non-integer, basically. It's not an own integer. Then this moduli space of spherical tori with one conical angle is a connected two-dimensional orbifold of early characteristic minus m squared divided by 12. So I think I have time. I want to like tell you what is this minus m squared divided by 12. So for this, you see, for this, maybe how can it be like non-integer, whatever? Like what we should really do is to understand the case of a flat torus, okay? So the flat torus is a very well-known object. It's called like modular curve. So you see, like this is like moduli space of flat torus is a modular curve. So like is so basically it's like this. Yeah, this is one. This is I times 1 plus I square root of 3 divided by 2. I think, yeah. This is I. So if you want to construct a torus, so what you should do, you put your you construct a lattice basically, yeah. Like this is my lattice inside of C. So this is my lattice, and then this is my lattice, and I get a torus. And basically, for every lattice can be constructed this way. So you put one point here and other inside of this figure. Okay. And this is like it's called modular figure or modular curve. And if you like, so this is M11, the 11, yeah. And and the only thing that you have to glue together these sides. So if you glue everything together, then what you get a surface which is like this, okay? So this point goes here, and I don't know, is there any color? So yeah, and this point goes here, okay? Now, why orbifold early characteristic of M11 is equal to -1 divided by 12? So it's like this. When we count orbifold characteristic, we need to count every point with its symmetry, yeah? And if you have a torus, any torus, yeah? Any torus has a Z2 symmetry. So a generic torus has symmetry Z2. Here we have symmetry Z4, and here we have symmetry. This we count with one divided by 4, and this is one divided by 6. Yeah. So this torus is like it corresponds to hexagonal torus, which has this symmetry. Yeah. So now, if we want to count orbifold early characteristic, so it's like this. We take our sphere. Sphere has characteristic 2. We subtract 3, yeah, 3 points, 1, 2, 3, and divide by 2. And this is equal to -1 divided by half, yeah. Here we should put back this point, +1/4, and with this point, +1/6. And I claim that this should be -1 divided by 12. Okay. I hope it's true. Yeah. Great. So this is what happens for the flat torus. But here we say that the orbifold early characteristic is -m squared divided by 12, and like so it's good because you see somehow we don't find a contradiction in its result, because if theta is close to 1, then we get the same number, -1 divided by 12. But finally, so this is a conference on special functions, and it's a kind of a joke, but I need to have a special function here, but maybe not the one which Alex would like me to have. But there is a theorem of Zagier and Harry is that orbital Taylor characteristic of the moduli space of Riemann surfaces is equal to zeta function of 1 minus 2g. Okay? And so kind of I kind of hope that this number somehow is maybe there is some kind, I don't know, who knows, maybe this result generalizes also to other genesis, who knows. Okay. Great. So now I will go a little bit like in the proof of the theorem, and the proof is like it's kind of some elementary geometry. So it has maybe 3 steps. The proof has 3 steps, and the first observation is really like again it's like it's totally is it so it's like this, that you see if you have a Euclidean triangle, yeah, you have a Euclidean triangle, you can ask a question, yeah, like when does this triangle contains inside of it the center of circumscribed sphere, circle, yeah, and the answer is kind of well known, yeah, like is if the triangle is obtuse, or sorry, if it is acute, then the point is inside, the center is inside of the circle. If it's on the boundary, if one angle is pi, then it lies on the diameter, and here we have an obtuse triangle, so it doesn't contain the center of circumscribed circle. So this is the fact that Euclidean geometry is kind of very trivial. But what is really kind of a new word about this is the following: is that you can reformulate this result in the following way. So Euclidean triangle contains a center of circumscribed circle if and only if it angles spherical triangle inequality. Like if the angles of spherical triangles satisfy triangle inequality, then the circle contains the center of the circle. The center of the circle is contained. So this kind of leads us to the notion of a balanced triangle. So balanced triangle is a triangle such that its angles satisfy triangle inequality. Okay. And the theorem, so the kind of the first kind of ingredient of the proof of the theorem is like this: is that if you take a spherical triangle like this, yeah, if you take a spherical triangle, then it contains a point which is on the same distance from its corners, if and only if the triangle is balanced. So this is the first result, and somehow you kind of have a proof here, more or less, on the board. So this is first hero of this of this proof: balanced triangles. Now, so the second part of the proof is basically so the claim is that somehow every torus can be glued from 2 balanced triangles. So this is the claim. But before stating it, I will give a slightly more, how to say, slightly more advanced statement. So you see, like if you have a torus, it might happen that the torus has an isometry, has a symmetry, and we call it a torus rectangular. If it has an isometric orientation, reversion, involution, such that the set of fixed points is the union of the circles. So here you see, here you have like this is my torus, and you have a symmetry which is rectangular, basically reflection with respect to this axis. And this reflection fixes this circle and also this circle. So this torus is kind of non-rectangular. It also has a symmetry, but this symmetry only fixes one edge. Sorry, one diagonal. Okay, so this is definition. So suppose you have a torus. Definition of rectangular torus. Sorry. And then here's the theorem. So we start with a spherical torus with one conical point of angle to pi theta, which is not odd. And then several statements. So first, it always has a unique isometry which preserves orientation. So this is very much like for flat tori, yeah. For a flat tori, we can always take a central symmetry. So it has this orientation preserving involution sigma central symmetry. Then, if torus is not rectangular like this, then it can be uniquely decomposed into triangles, into balanced triangles. So it can be glued from two isometric balanced triangles. And finally, if it happens that the torus is rectangular like here, then you see it can be glued from two triangles in two different ways. And this is the basically main result from which this kind of from which basically this theorem follows. Like maybe I will show this just the last slide where I will show like, so what should be done next. So what should be done next somehow is you so you remember that we had this picture with tetrahedrons, yeah, which is like this. The picture with tetrahedrons inside of like the whole R3, a periodic one. And what we need to do basically, so we need to understand here where the balanced triangles lies. So what we do, we take kind of a plane here. We intersect with collection of tetrahedrons, and when we intersect, we get something like this. You see, like we get this picture. Intersection of a plane with a collection of tetrahedrons. Kind of this pretty picture, you can see like the number of triangles grows quadratically. And more or less, this is the moduli space of surfaces of genus 1. And the only thing that you need to do, you need to kind of, this doesn't look like a surface, but what you need to do, you need to make a real blob here. And then you get a surface of Euler characteristic minus m squared divided by 12. Yeah, so I think that's it. And Alec, happy birthday.
Any questions?
No,
Yes.
I have just a historical comment. So the theorem for non-positive curvature, which completely solves the question, it is actually due to Picard. So Picard wrote 4 papers in the book about this theorem. The first paper is of 1870s, so it is well before the uniformization theorem. And the book in 1930, which contains this result. Of course, Picard's arguments, Picard's exposition, I would say, doesn't satisfy the modern standards. But there is another paper to which Oleg Ivry referred yesterday, is by Morris Hines of 1962, where the result for non-positive curvature has been completely established in a rigorous modern language.
Thank you.
Thank you very much. Any other questions or comments? Yes, please.
You get it right that the spaces MSPH GN in general, they don't necessarily have a manifold structure, but they have orbifold.
Yeah, but this is basically very similar to MGN as well, because it's just like, so they're almost the best that they can hope for is an orbifold. It just and MGN itself is an orbifold, and this is the reason is basically that if you have a Riemann surface of genus, it can have symmetries, finite number of symmetries, and produce orbifold points. And here, basically, it's totally parallel. So you can prove that it's also a kind of orbifold almost always.
Okay, thank you very much. Any other questions or comments? Okay, organizers are asking to remind participants first to return the cards, and second to sign the poster for Alex. So we have now half an hour break. This hopefully, and we can use this time to sign a poster. Thank you very much. Okay, and we will continue at 4:30.
Yeah, well,
And this is his. That was a long. Small one.